SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 3, that is Gas Turbines and Combined Power System. So, in the last lecture of this module, we will try to emphasize the importance of gas turbines as a propulsion device. So, till this last lecture, we have been giving emphasis on the gas turbine engines as a power production device. In this lecture, we will try to see that how gas turbines can be used as a propulsive device. Although this is not the part of this course, but as a continuation of gas turbine systems, it is felt that we should give some emphasis on the gas turbine applications as a propulsion device. So, in this lecture I will briefly introduce this gas turbine cycles as aircraft propulsion cycle. In addition to that, I will try to demonstrate a simple turbojet engines in which gas turbine concepts were introduced, and through this process we will see that how the thermodynamic concepts will help us for the gas turbine engines as a thrust generating device. Then we will also introduce some of the aircraft engines, in fact that are also driven by this gas turbine engines. So, if you look at the basic cycle of gas turbine system, we have like a compressor, turbine, combustion chamber, air is fed into the compressors and it is after compression high pressure air and to some extent temperature also increases. It enters to the combustion chamber in which fuel is added. So, this is the heat addition process, and then the combustion after combustion chamber the gaseous products expands in the turbine. And here we have two options, that from this exhaust gas we can find or we can use this exhaust gas to generate this thrust. But with the conventional turbine, because turbines are meant for power productions, that is what it is coupled to generator, and side by side it is coupled to compressors. So, these are power production devices, but that cannot be used, means same kind of components cannot be used for thrust generations. So, you require some kind of modifications, and that modification we call them as aircraft propulsion cycles. So, this particular cycle which is shown in this figure, we call it as a soft power cycle, and this is something like static power plants, gas turbine plants, typically land, marine engines, combined cycle power plant, all these things. And for aircraft propulsion cycles, we expect that it should give the thrust and it should give you the forward speed and altitude dependent, because this propulsion cycles is also altitude dependent. So, some modification that need to be done for these conventional gas turbine cycles to be used for propulsion devices. However, the soft power cycles, we have seen many kind of modifications in the soft power cycle like multi-stage compression, expansion, heat exchange, reheat, intercooling. So, these are kind of improvements in production of power and efficiency. But our main attention in this lecture would be how gas turbine cycles are used for as a propulsion device. So, let us try to understand the very basic concepts, that Here same Brayton cycles was modified in two forms. So, we have the we have two concepts here, one is called jet engine concept, other is called propeller engine concept. So, in a jet engine what happens, air comes to the compressor, it is compressed, and in the combustion chamber you add fuel. So, we get the combustion product at state 3 and it expands, and after expansion you just do two things, one is turbine whatever power is being developed that is to be used by the compressors, and whatever expansion of the gas that we can feed it to a nozzle, and this nozzle after expansion it will give you the thrust. So, this exhaust gas, that means this is something like Newton's third law of motion. So, when the exhaust, for every action there is an equal and opposite reactions. So, when the exhaust comes back at the state 5 and if this entire gas turbine system, if it is taken as a single system, so aircraft velocity we can get this way. So, we get the thrust in the other directions, reverse directions. So, here the changes that we see, we can see that compressor process remains as it is, but here expansion is done in two stages, one is for turbine expansion, other is through the nozzles, and this is shown as 1, 3, 3, 4 is the expansion in the turbine and 4 to 5 is the expansion in the nozzle. But only difference is that now turbine expansion gives you power, expansion in the nozzle gives you thrust. This is one concept, and the propeller engine concept, this is also similar things. Here we do not have a nozzle there, but rather exhaust goes out and that through that exhaust we get some thrust. Side by side we have a propeller, and the propeller roll of the, we have a propeller which is driven by these turbines. So, essentially turbine plays the dual role, once is some bare minimum due to the exhaust velocity we get one thrust, other thing is that or primary thrust which is being achieved through the propeller, and the power driven by power is supplied from turbine to compressor as well as the propeller. So, we do not have a two stage expansion, we do not have a nozzle here, rather single stage expansion in the turbine solves the purpose, but they have their own limitations and applications. So, what we have is here we have at lower speeds, that is less than 200 meter per second, combination of propeller and exhaust gas provides propulsive efficiency, we call this as a turboprop engine or propeller engine. At very high subsonic speed, maybe more than 280 meter per second, we have another device we will call as turbofan or bypass engine. So, we will talk about later that, but actually the jet engine which is given by these things, it is called as a turbojet engines, which is somewhere fall between a turboprop engine and turbofan engines. So, in a turbojet engines we have a turbine that produces enough power to drive the compressors, and gas leaving from the turbine at high pressure and temperature is expanded to atmospheric pressure in a propelling nozzles. So, this is what we have. Another engine that we have is like we have a turbo shaft engines, they are normally used in the helicopters, but very basic other difference that we can have is we do not have provisions for heat exchanger in aircraft propulsion systems, because these units make the system very bulky and weight, and it will add more weight that normally it is not expected for aircraft engines. Rather, propelling nozzles and propellers, they are integral part of gas turbine engines. So, our main focus would be on these two kind of nozzles, diffusers. These devices are more appropriate for gas turbine applications. So, let us try to consider very simple classical example which is just to demonstrate Newton's third law of motions or mainly Newton's law of motion. First thing is that rate of change of momentum is the force. So, this is that means entire thrust is being generated from through the rate of change of momentum for the gas. Then another law says that for every actions there is equal and opposite reactions. So, for that by using these two things, we now think this power unit, this power unit is in this figure what is shown is power unit is your gas turbine cycle, or which is which supplies necessary power to the aircrafts. So, we call this as a propulsive duct in which air enters at certain velocity which is equal and opposite to the forward speed of the aircrafts. So, basically air enters to the duct, so we call this as a, so this is power unit, or we call as a propulsive duct. Now, in this propulsive duct, this power unit is nothing but your gas turbine engine. So, that is that way we model it. So, in this, if you take this entire unit as a single entity, we see that air enters to the duct at a velocity Ca, we call this as intake air velocity, and air the leaves at not air, maybe combustion products leaves at velocity which is called as exit jet velocity. So, we call this as a two velocity, one is air velocity, other is jet velocity. So, m dot Ca stands as intake momentum or drag, and m dot Cj, drag means it is the force that being experienced by this duct. Then m dot Cj is the gross momentum thrust, that means that jet that gives the thrust that when it comes out. So, resultant thrust becomes m into Cj minus Ca, we call it as a momentum thrust. So, the momentum thrust is nothing but m times Cj minus Ca. So, the net thrust now becomes momentum thrust. There is another thrust that comes on, that comes due to the pressure difference. So, essentially the aircrafts are flying at very high altitudes, pressure is less, and side by side there is also a pressure difference in the on the surface. So, ambient pressure and the pressure which is on the surface of the aircraft, there is significant difference. So, these thrust add to the fact we call this as a pressure thrust. So, these two thrust, net thrust necessarily gives the total thrust onto the vehicle, but however at lower speeds the pressure thrust are not significant. We normally call it as a momentum thrust, which is nothing but F is equal to m times Cj minus Ca. Now, putting this net thrust that comes these things, we define the propulsive efficiency, which is defined as the propulsive useful propulsive energy to the sum of the energy and unused kinetic energy. Essentially speaking, when air enters, it has a kinetic energy, and when air leaves, it is also has some kinetic energy. So, the entry energy and leaving energy, they are equated by this energy balance with the fact one energy that gives you the thrust, necessary power for this thrust, other energy which is we call is a unused kinetic energy, that also gives you necessary enthalpy difference between entry and exit state. So, that part if you actually calculate, we call this as a unused kinetic energy. So, this we can define a term which is called a propulsive efficiency, which is defined by this ratio. Now, this equation gets simplified. So, we say that propulsive efficiency eta P is equal to twice time by 2 by divided by 1 plus Cj by Ca. One significant inference that we can see here, that when Ca is equal to 0, F tends to maximum and propulsive efficiency becomes 0. When Ca is equal to Cj, F goes to 0 and propulsive efficiency becomes maximum. So, this gives two concept of a propeller jet and or a jet engines. Now, what happens is that we require a balancing approach between Ca and Cj such that at a given speed we get best propulsive efficiency. So, thereby we use the concept of propeller or jet engines. For example, if you use a propeller driven engines, it has efficiency much higher than the jet engine, but beyond certain limit, beyond certain aircraft velocity, let us say maybe 500 kilometer per hour. So, this propulsive efficiency drops. That means, propeller concept does not work beyond this number, beyond this aircraft velocity. But still, if you want to travel faster, then you have to use the other concept, that is called jet engine. So, higher speed means jet engine is the best approach. Lower speed means propeller driven engine is the better approach, because they give best possible propeller efficiency. So, this is how we use this is how the jet engine concept comes into pictures. So, one such simplified jet engine, we call this as a turbojet engines, and this turbojet engines idea comes from the aircraft comes as aircraft propulsion cycle, and its main idea intention starts with gas turbine engines, because they favor high power to weight ratio, and when you say turbojet engines, we can expect higher power at relatively lower weight. We also try to emphasize that we are not using any kind of heat exchanger or bulky devices to make it unnecessarily bulky or increasing the weight. So, essentially when you say this turbojet engine, it has few main sections. One is called as a diffuser section, second is gas generator sections, and third is the nozzle section. So, if you look at this particular figure, we have shown in three sections here: diffuser, gas generator and nozzle. And some important events that happens at various locations, and locations are noted as A, 1, 2, 3, 4 and 5. So, these numbers essentially says that when air enters into this engine, it passes through different components. So, the first component that it enters is the diffuser. What does it do? It increases its pressure at the cost of velocity. So, velocity when it velocity drops. So, initial velocity is high. So, it drops to 0 velocity ideally. So, when it enters to the compressor, air relatively velocity is relatively close to 0, and when it enters the compressor, the pressure shoots up. So, 1-2 process, we call this as a compression process. So, first process it starts with A2 1 is the process in the diffuser, in which we can see rise in the temperature, but and rise in also pressure from P A to P 1, but drop in the velocity, and from 1 to 2 is the compression process. So, it goes in this manner, and ideally we can see this process, entire process to be isentropic, both in the diffuser as well as in the compressor. Now, similar to this, air enters to the combustor, where heat is added. Essentially here we add fuel. So, in this cycle we can see that we add Q in, heat added into this fuel through by means of fuel. So, 2 to 3 is your heat addition process at constant pressure, then it enters to the turbine sections. So, the turbine section when it enters, and expansion has done in 2 stages, one is turbine, other is nozzle. So, we have 2 sections here, one is from 3 to 4, that is turbine, and 4 to 5, that is nozzle. Similarly, the entry A to 1 is diffuser, and 1 to 2 is compressor. Okay. So, so expansion, and there are 2 expansion, but this first expansion is just to produce power, second expansion in nozzle is to produce thrust, and finally the combustion product goes out at certain velocity. So, when the combustion products leaves the turbine at a pressure significantly greater than atmospheric and expands in nozzle to very high velocity before being discharged to the surroundings. So, the overall change in the velocity relative to the engine rises the propulsive force or thrust. So, this change rate of change of velocity gives rise to, and when it is multiplied the mass of the system, it gives the necessary thrust, and we call this as a propulsive force and thrust. But there are some advanced turbojet engines. We have similar components like diffuser, gas generator, nozzle, but additionally we have some units like afterburner. So, the role of afterburner here, because since it should be emphasized that jet engines are mainly intended for thrust. So, we require the efficient usage of fuel. So, that is the reasons entire fuel is not added at the combustor itself, rather they are added, some fuels are added in the combustors as a primary fuel, and some other fuels that gets added in the section which is in the afterburner, and we call this as a secondary fuel. So, in order to have efficient use of fuel, different sections like we have a combustor and afterburner section for addition of the fuel. So, through this process we can get an enhanced or increased thrust. So, now let us more details we can explore in various other aircraft propulsion systems, but in this particular domain or in the framework of our syllabus, we will just try to explain the thermodynamic aspects behind a gas turbine cycle which is used as a propulsion device. One such simple cycle is the turbojet cycle, and we call this as a turbojet engine. So, an ideal turbojet engine has 5 basic components: diffuser, compressor, combustor, turbine and nozzle. So, the process starts with A21. A21 means it is a diffuser, that means air inlet to the diffuser, and what does this diffuser do? It diffuser, the pressure increases at the cost of velocity. So, at the end of the diffuser, ideally the high speed air velocity comes to the to kind of a zero velocity. That means, entire energy from the entire energy of air gets converted to the pressure energy. So, we get at state 1 P1 pressure, and that is supposed to be higher than PA pressure. You can also see here. So, PA and P1, P1 is already higher pressures. So, after diffuser air enters to the compressors. So, thereby the compressor load is also decreased. So, 1 to 2 process now becomes the compression process. So, 2 to 3 is your combustion process, in which we add constant pressure heat addition. So, we add Q in, that is Q in comes here, and after this we have 2 stage expansion. The first stage expansion is 3 to 4, that is turbine, and second stage expansion is from 4 to 5, that is nozzle, and finally the exhaust goes out. So, because since it is both side it is open to atmosphere, so there is it is not a closed cycle. So, so finally the process stops at 5. So, there is no arrow from 5 to A. So, diffuser in the diffuser there is a rise in the pressure due to deceleration of air. In the nozzle there is a drop in pressure due to acceleration of air. And analysis is, but however, this is just a thermodynamic estimates, and we also encounter steady flow of analysis based on the first law of thermodynamics. So, however, real cycles will have different numbers when the components efficiency comes into pictures. So, that is the reason, owing to irreversibility of actual engines, there would be increase in the specific entropy. So, process need not be an isentropic process in the diffuser, compressor, turbines or nozzle. and of course, there is a possibility of combustion irreversibility, pressure drop in the combustors. So, all sorts of things will be taken care when you actually take an aircraft propulsion course separately. But our viewpoint is different. So, here in this lecture I will just try to see the thermodynamic estimates, which is not an accurate number, but it can give you, based on our thermodynamic analysis, we can find some estimates. Actually, estimates means typically what type of velocity range we are looking at for a gas turbine engine. So, assumptions goes like components of an ideal turbojet, they operate at steady state, except at the inlet and exit of the engine. Changes of kinetic energy and potential energy effects are negligible at all other locations. The classical steady flow energy equation we use like this, and other important expressions that you can see: velocity at the exit of the nozzle for diffuser expressions. Ideally, when you say jet engines, normally this particular relations holds good. Turbine drives the compressors. So, turbine work generated by the turbine is equal to work consumed by the compressors. So, with these working equations, this we can solve this jet cycle, turbojet cycle. So, apart from this, there are other types of engines that are available. First thing, we have two main category. One is the lowest. When you operate at lower speed, we have a turboprop engines. So, turboprop engines you see here, we have a propeller here. So, most of the aircrafts, wherever you see these things, rotating device, we call this as a propeller. And the other extreme case is that where there is no turbo machine devices, it is a simple duct, and in duct and whatever pressure difference that is created, that is through this geometry of this duct. So, we call this as a ramjet engines. So, this shape of this duct essentially changes the pressure and temperature conditions within the medium. So, and when there is an increase in the pressure, with this increase in the pressure conditions, fuel is supplied. This is nothing but your flame holder where fuel is supplied. And finally, the jet expands. So, to run a ramjet engines, we have to pass through these stages. Like we can we initially run the engine to some speed, then allow this ramjet engines to fire. So, we have seen the classical engine, turbojet engine, which is the very basic, and initial version of that was turboprop, but in order to improve those efficiency of propeller and jet engines, we also have another engine called as a turbofan engine. So, what does this do? We do the same concept with additional change in the structure or location of devices. We are introducing a kind of a bypass flow. That means, we will have a one flow that goes in the engine core, other flow that goes out, and they finally meet in the end, and where that fuel that air and that fuel gets added in the afterburner to generate extra thrust. So, we call this as a turbofan engines. So, these are the kind of jet engines which are available as of now on a commercial viewpoint. So, turboprop engine consists of gas turbines in which gases are allowed to expand through the turbine at atmospheric pressure, and here net power is directed to the propeller which provides thrust. And typically the turboprop engines, their capability is up to the speed 850 km per hour. Now, for turbofan engines we add extra attachment where we are using nozzles, first thing. Second thing, we also have two things, one is a core air movement, other is bypass air movement. So, through this process additional thrust enhancement is done, and for which we can achieve speed up to 1000 km per hour. A special type of engine, and of course, it is simple engine, but flow physics is very complicated, and this simple engine is without any turbo machine components, and we call this as a ramjet engines. So, what is this ramjet engine? When we have a sufficient pressure rise in the air inlet or duct systems, the decelerating effect of high speed in air in the diffuser is known as ram effects. So, that is the reason we call this as a ramjet engines. So, for a ramjet engine to operate, the aircraft must be in flight at high speed, and initially it has to be powered through a conventional jet engine, and subsequently ramjet engine has to be fired. And here what it gives, due to this ram effect, the combustion products are expanded to in the nozzle to produce very high thrust. Another important aspect of all these engines, they are called as a air breathing engines, because they breathe air to run the systems, gas turbines. But and all these jet engine or aircraft propulsion devices, they are air breathing engines. But at very high altitude or space travels, this is not possible, because at very high altitude or in the space there is no air. So, we require separately fuel and oxidizers, typically in the liquid oxygen, and thrust is produced when high pressure gases are obtained on combustion and expanded through nozzle and discharged to the rocket, and they are known as non air breathing engine or rocket engine. So, rocket engines are not air breathing engines, they are non air breathing engines. But however, these concepts are of different notes. So, it is better that we are not going deep into these concepts, but our main attention or focus of this lecture is to demonstrate this gas turbine cycle as a thrust production device. So, with this I come to the end of this lecture, but before we disperse, let me introduce the problem which based on the analysis of our turbojet engine. So, the problem statement goes like this. So, here I have given the sketch of a turbojet engine. This air enters the turbojet engine at 0.8 bar and 240 Kelvin. So, inlet conditions is fixed at I will say PA is equal to 0.8 bar and TA is equal to 240 Kelvin. Side by side we know this particular location. Pressure ratio in the compressor is 6, like after exit from this diffuser, because it enters the diffuser, after exit from the diffuser it reaches to state 1 and entry to the compressors. So, that number we do not know, but P2 by P1 we know it is 6, sorry, P2 pressure ratio in this compressor is 6. Turbine inlet temperature is 1200 Kelvin. So, at condition T3 we say 1200 Kelvin. Work developed by the turbine is equal to compressor work. So, we say W dot C by M dot is equal to W dot T by M dot. Turbine drives the compressor. The flow processes are isentropic in all the components, like we have diffuser, compressor, turbine and nozzles, they are isentropic processes. There is no pressure drop or flow in the there is no pressure drop in the combustor. At steady state operations, we need to determine the velocity at the nozzle exit. So, essentially we are looking at what is velocity at state 5 at this nozzle exit, that is the question mark. And also we expect what is the pressure at each principal stage, like what is P1, P2, P3, P4 and P5. Okay. So, to start the problem, let us do component wise. First thing, you recall the equation for diffuser. So, the flow equation, the diffuser has two parts. One is we can say because what this diffuser does, after the air and reaches at the end of the diffuser, the velocity becomes 0, entire kinetic energy is converted to pressure energy. So, we can write these equations like P A plus half rho V A square is equal to P 1 plus half rho V 1 square. So, this becomes 0. So, and we know P A that is 0.8 bar, V A 1000 kilometer per hour, and that is 1000 into 5 by 18, that becomes 278 meter per second. So, we can find out what is P 1 is equal to 0.8 means 80,000 plus half rho you take as 1.2 for air kg per meter cube, V A is 278 square. So, this turns out to be P 1 to be 126.3 kilonewton per meter square or kilopascal. Then we also expect what is temperature as well or enthalpy as well. We can write enthalpy equation as H A plus V A square by 2. Of course, your velocity at state 1 is 0. So, V 1 square is 0. So, total enthalpy now becomes C P times T A plus V A square by 2. So, V A is known, temperature, T A, temperature is given as 240. So, T A is 240 Kelvin, take C P as 1.005 kilojoule per kg Kelvin, and we have V A 278 meter per second. So, this will give you H 1 as 279.8 kilojoule per kg. Then we have compressor. Compressor with equation you can write T 2 by T 1 is equal to P 2 by P 1 to the power gamma minus 1 by gamma. So, P 2 by P 1 given as 6, gamma 1.4. So, this means 6 to the power 1.4 minus 1 by 1.4. So, this number is 1.66. So, this will give you now we do not know T 1. So, we can, but we know H 1. So, H 1 means H 1 is equal to C P times T 1. So, this will implies T 1 is equal to 1279.8 divided by 1.005. So, this number is 278.4 Kelvin. So, we know T 1, we know this ratio. So, this will give you T 2 is equal to 463.9 Kelvin. Then we move to turbine. So, for turbine we write the working equation, that is W T by m dot is equal to W C by m dot. So, this becomes H 3 minus H 4 is equal to H 2 minus H 1. So, for all the numbers we know that we have calculated H 1 is 279.8 kilojoule per kg. We have H 2, that is C P times T 2, and we have H 3 C P times T 3. So, T 3 is your T 3 is our 1200 Kelvin. So, knowing this, we can arrive at the expression H4 is equal to 1019.6 kilojoule per kg. Okay. Then we move on to, from turbine we go move to nozzle. So, for nozzle we can say the working equation V5 is equal to twice times H4 minus H5 whole square root. So, we have already H4, we do not know H5. H5 is nothing but Cp times T5. So, when you say T5 and Ta, this is Ta, that is entry, exhaust also goes to atmosphere. So, we can say it is T5. So, T5 and Ta we can assume it to be ambient. So, Ta is already given 240 Kelvin. So, we can say T5 to be approximately 240 Kelvin. So, Cp times T5 becomes 241.2 kilojoule per kg. So, V5 we can now find out twice into 1000 into 1019.6 minus 241.2 whole square root. So, velocity V5 is now becomes 1247.7 meter per seconds. So, we say velocity at the exit is 1247.7 meter per seconds. But what extra things that we require? Pressure at each principal state. So, we have already noted down various pressures at all other components. What we have not noted down is P4. So, P4 that can be calculated from this turbine working equations. Like, so again for turbine we can write T3 by T4 is equal to P3 by P4 to the power gamma minus 1 by gamma. So, we know T3 that is 1200 Kelvin. We have T4 is nothing but we have H4. H4 is equal to Cp times T4, that is equal to 1019.6. So, this kilojoule per kg. So, T4 we can find out as 1014.5 Kelvin. So, from this we can find P3 by P4 is equal to 1.78 and P3 is nothing but P2, which implies P4 becomes 4.25 bar. So, ultimately at the end of our analysis, if I express my answers in a single chart, what I can say? Pressure at each principal states. So, we can say Pa, which is ambient pressure at 0.8 bar, which is given. P1 exit from the diffuser we have already calculated to be 1.263 bar. P2 after compression of pressure rise 6, we say P2 is equal to 7.58 bar. P2 and P3 are equal, so we can say P3 is also 7.58 bar. P4 in the last slide we have calculated, that is equal to 4.26 bar, and P5 is again atmosphere or ambient conditions, that is Pa 0.8 bar. So, this is all about the pressure conditions at all principal states in the cycle, and finally, what is the velocity V5, that is equal to 1247.7 meter per seconds. So, this demonstrates that jet velocity is too high to give necessary thrust through this concept of gas turbine cycle implemented in this turbojet engines. With this, I conclude this module. Thank you for your attention.